Hi, everyone. I wanted to go over an example. This used to be a quiz problem. I used to do quizzes in this class. I was thinking of putting this in a homework, but you already have plenty of homework problems. So I decided I will just turn it into an example. So here's the example. The top plots in the figure show a wave function at some moment of time, and its Fourier transform A of k at that instant. So the time is suppressed because this is all shown at the particular time instant. Okay, so normally both functions are complex, but for the purpose of this problem, we'll pretend that they're real. And then the bottom plot shows a different wave function, psi2. In question A, it says, make a sketch of the Fourier transform of that psi2. Make sure the horizontal x-axis has values. Okay, so I'm gonna use the draw feature. Pause this video and make a sketch in your own notebook or whatever you use. What do you think it will be? Fine, I will just, to make sure that we get the same scale, I will do this. So it's very common that I ask you to draw one graph underneath the other. And I would like you to show the scale in the second graph so I know how your predictions or how your graph compares with the other one. So we are comparing apples to apples. Okay, so this is now what, 2 pi, this is pi, and this is 3 pi. The x-axis is k, and the units are radians per nanometers. Radians aren't real units, so this is why it's nanometers inverse. This is very similar to one of your homework problems. So what would you draw here? How would you reason out? Well, here's how I would reason this out. I see that the dominant wavelength in psi2 is clearly twice as big as the dominant wavelength in psi1. It's not the only wavelength because it's not a pure sine wave, but clearly the dominant wavelength is twice as big. The dominant wavelength or the dominant k, the dominant wave number, is the center of the Fourier transform, is the peak of the Fourier transform. And since the dominant wavelength is twice as big, the dominant k is twice as small. So the peak of the Fourier transform will be not at 2 pi per nanometer, but at pi per nanometer. So it will be centered right here. When I gave the students when I gave this quiz, a lot of students missed this. This is point number one. The second point is, what about the width of the Fourier transform? Well, the width of the Fourier transform encodes in it the overall width of the function in real space. So this is k space and this is real space. We see that the overall width of psi2 is actually the same as the overall width of psi1. So if you, in your mind's eye, mentally draw the envelope around psi2, and you look at the width of that envelope at half of its maximum, it's actually the same as psi1. It's about, I don't know, it happens at maybe about 1.5 nanometers or something like that. So since the width of the wave function is the same, the width of the Fourier transform is also the same. So all in all, I would draw something that looks like this. It's basically the same Fourier transform, but it's shifted over to be centered on something like that, okay? This is very difficult to draw, especially difficult to draw on iPad, but I would draw something like that. Same width, centered on pi per nanometer, okay? Part B, a large number of experiments are performed on identically prepared particles. In each experiment, a position measurement is taken when the particles are in the state described by the wave function psi in top picture. Draw the probability distribution of measured positions. Make sure to label the axes and include tick marks with numbers. Don't rush, think carefully. So let me speak through it or talk through it, and then I will pause, I will make a drawing, and I will show it again. So how would you do this? A lot of students missed this, a lot. Almost everybody missed. The question concerns the probability distribution of position. How do we get the probability distribution if we know the wave function? Well, it's the square of the magnitude of the wave function. In this case, the wave function is real. So that's the same as the square of the wave function. So all I have to do is I have to square psi. And that will be my probability distribution. Okay, so this is my masterpiece. Not very good, but gets the point across. So everything that was a negative peak becomes a positive peak, and everything that was a positive peak, well, it's still a positive peak. Let's see, to the right of the center, I have 1, 2, 3, 4, 5, 6, maybe 7. I try to do this same thing. 1, 2, 3, 4, 5. Okay, so there will be 6, and so on. Well, it's not a very good drawing, but really the number of peaks should be about the same. When you square something, it distorts. Something that's bigger than 1 is increased, something that's smaller than 1 it's suppressed. But the point is, the probability distribution is going to be just the square of the wave function. I'm not putting the bars because it's a real wave function. We don't have to take its magnitude first and then square. A lot of students, what they drew is they drew just a bell-shaped curve. The actual square of the wave function is this thing. Now we can talk about its structure. Well, it has a broad structure. Okay, that's the envelope. The envelope is not, it's just a way to guide the eye to the broad structure. The actual wave function is the one that's the non-dotted. Right? So you see, so this is the envelope. And it is, and a lot of students just drew the envelope, but they did not draw the wiggles. I'm not sure why. So this example is here to alert you of that. So what does it mean? Again, physically, what does it mean? It means when you do prepare a bajillion particles, each in the wave function described by this psi, and then you start measuring away their positions, you're going to get a distribution that looks like this thing. And you will get accumulation of particles here, accumulation of particles here, accumulation of particles here. The biggest mountain of particles, or the biggest accumulation of particles will be here. There's also a pretty decent accumulation of particles here, fewer here, and so on. And there will be spots where you're not going to find any particles, right? So there will be spots that are right here. You will never find particles there. That's the statistical interpretation of this wave function psi right here. Okay? Well, the next question is, what is the most likely measured position of a particle? Again, you have statistics. You have an ensemble of outcomes distributed according to this probability distribution. So you can talk about averages, you can talk about standard deviations. The most likely measured position of the particle is going to be the one where it will be such position where the probability distribution is maximum. Where's probability distribution is maximum? Well, it's maximum with x equals 0. So the most likely value is going to be x equals 0. This is the most likely value. Don't confuse the average with the most likely value. They're not always the same. I can have a distribution that's asymmetric. The most likely value is here, but the average is somewhere here. For symmetric distributions, most likely value is the same as average. For asymmetric, not the same. Okay, next question. The standard deviation of position measurements is approximately this value. And it says you can estimate it from reading off 1/2 of the full width at half maximum of the envelope of the probability distribution. A little preamble. What does it mean precisely? What does it mean? What does the standard deviation mean precisely? Well, precisely, the standard deviation of position measurements is really this thing. This is the precise definition. And it's a measure of the spread of the distribution. Now, in this case, x bar is 0. So in this particular case, it's the square root of the average of x squared. you still have to keep the square root because you average the x squared. It's not the square of the average. How do you compute the average of x squared? What is this thing right here mean? Well, the average of x squared is the following thing. Notice I'm using capital P so you don't confuse it with momentum. So to actually compute this thing, you have to take this function, the wiggly one, this function, multiply by x squared and integrate. But I didn't give you that function. Okay? So therefore, you cannot actually compute it exactly. What I'm suggesting to you is I'm suggesting ignore the details, ignore the fine details of that function. Just squint your eye and approximate it by the envelope. And if this function is Gaussian, we know that half width at half maximum is very close to the standard deviation. So in this suggestion right here, it's implied that A, you can ignore the wiggles and you can just, that you can compute this integral, this thing right here, by approximating the function by just its envelope. It's not obvious, I'm just telling you to do that. And second, it's saying, well, you can actually extract the standard deviation by going to half of the maximum, looking at the width, and divide by 2. And that's not true for all distributions, but if it's a Gaussian, it's very closely true. Okay, we saw that in yesterday's lecture. Okay, so long story short, when I do that, here's the maximum, here's half maximum. Okay, so this is right here. So it's close to 1. Okay, so here's half, maybe half maximum is here. And so I read off at half maximum and I say it's close to 1 nanometer. 1 nanometer. It's an approximation. And when we gave this as a quiz, we were pretty lenient in what students said. But again, so this is the maximum, this is the half maximum, the width at half maximum comes out to be 1 nanometer. Now, question C. A large number of experiments are performed on identically prepared particles. And in each experiment, a momentum measurement is taken when particles are in the state described by the wave function psi. Right? Okay, so we're talking about this business right here. We actually give you both the wave function and its Fourier transform. And the question is, what is the most likely momentum measurement? And how do you see it both from the psi and from the Fourier transform? Well, I think it's actually easier to see it from Fourier transform directly because you can see here that A of k is largest at 2 pi per nanometer. And so when we take into account the de Broglie relationship that P equals h bar k, that means the most likely momentum that you would get from measurement is h bar times 2 pi per nanometer. Okay, so that's going to be, so this is going to be 2 pi times h bar. And I'm going to put the units. So this is 6.6 times 10 to the minus 23 per nanometer, 10 to the minus 9 meter. What are the units of the h bar? It's meters squared, kilograms over seconds. And when the dust settles, I get 6.6 times 10 to the minus 25 kilograms meters per second. So once again, I look at A of k. I remember that the statistical meaning of A of k is such that the square of the amplitude of A of k is proportional to the probability distribution of momentum measurement outcomes. And I have to include the h bar because that's how you convert from k to momentum. The most likely value of momentum is going to be h bar times 2 pi per nanometer. So here it is, 6.6 times 10 to the minus 25 kilogram meter per second has the right units of momentum. How do you see it from the wave function? Let's say I didn't have A of k. Well, I look at the wave function, I see, well, it's not a pure sine wave, but it's a pseudo sine wave or a quasi sine wave that has clearly 1 nanometer wavelength present in it. And I say, aha, well, so the dominant wavelength it's not a pure sine wave, but the dominant wavelength is 1 nanometer. Okay, so wavelength dominant is approximately 1 nanometer. So K dominant is 2 pi over the wavelength, right? 2 pi over wavelength dominant equals 2 pi per nanometer. That's the dominant wave number. And to convert it to momentum, again, I multiply it by h bar. So 2 pi per nanometer times h bar, and I will calculate the same number. Okay. The standard deviation of momentum measurements is approximately this value. Again, you can assume that A of k is Gaussian. Also make sure the units are right. Judging the standard deviation by width and half maximum, again, same idea. It's really width at half maximum of A squared, or the square A of k magnitude squared. That's really the probability that gives the probability distribution for momentum. And so judging the standard deviation as 1/2 of the full width of this quantity, and then multiplying by h bar, the answer will appear to be, well, this is, let's see, this is pi, this is pi, so this is maybe pi over 2. Between pi over 4 h bar to pi over 2 h bar, depends on how you measure, right? So pi over 2 h bar per nanometer to pi over 4 h bar per nanometer. It's not, you're only given the graph, right? So it's very hard to see it from this graph. I think it's closer to pi over 4. And also remember that it's not A of k that matters, it's the square of the magnitude of A of k. So that's gonna stretch it a little bit. And so that's gonna make it closer to pi over 4 rather than pi over 2. And the last thing it's saying is to multiply a pair of quantities to explicitly check explicitly that the uncertainty principle holds for a particle prepared in a state given by the top wave function. So what is it that we have to multiply? So check Heisenberg uncertainty principle means, well, you multiply these two things. Okay, and so this gives me spread in the x values is 1 nanometer, as we just established. Okay, this right here. Spread in the y values, I'm sorry, spread in the momentum values, pi over 4 nanometer times h bar, and I get pi h bar over 4, which is approximately 0.75 h bar. 0.75 h bar, which is a bit larger than the theoretical minimum. This is a little bit larger than 0.5 h bar. It's a bit larger than the theoretical minimum. However, keep in mind that our estimates of sigmas are approximate. I didn't actually compute integrals, I just eyeballed quantities. And if I did, I would still get it. I would get a number that's certainly bigger than this theoretical minimum. When students were asked to do this, what we really paid attention is that students knew what to multiply and what to check it with. Okay, so this is an example. Hopefully it's useful for you. Okay, well, see you later. Bye.